Welcome back. Let's learn about partial derivatives. All right, it's time. We're going to start looking at how to find derivatives of multivariable functions. But what exactly does the derivative of a multivariable function look like? What would it represent? What would we actually be doing? Well, remember from Calculus 1 that the derivative of a single variable function is the slope of the tangent line to the curve at a point. So extending this to multivariable functions, such as functions of two independent variables, f of x, y, since we know that represents a surface in 3D, we would naturally think that the derivative would be the slope of the tangent line to the surface at a particular point. But is it that simple? Well, let's take a look here. For this point on this particular surface I have drawn here, which is half of a sphere or a semisphere, you could draw a line tangent to that point that looks like this. That would be a tangent line to that point. You could also draw one like this. That would be another tangent line. And you could draw one like this. That would be another tangent line to that point on the surface. And we could keep going. I could draw one here. I could draw one here. I could draw one here. It never ends. We could keep drawing more and more lines tangent to that point on the surface. We are not limited to one single tangent line to a point on this function like we are for single variable functions, right? There's only one line that you could draw tangent to a point on a curve. There's only one line that would take the slope at that point and extend it with a line. In this case, for a surface, there are multiple different directions that we can consider for drawing a tangent line. Depending from which direction you approach that point along the surface, there are different slopes that that tangent could take and extend forever with a line. And so unfortunately, derivatives of multivariable functions are not as simple as just being the slope of the tangent line to the surface at a point. That's too ambiguous. It's not clear enough because there are an infinite number of tangent lines at a point on a surface. And note that I am talking about tangent lines here, not tangent planes, which is something different. We look at that later in Calculus 3. Right now we are talking about tangent lines. And so because there are an infinite number of tangent lines at a point on a surface, we have to take a different approach to what it means to find a derivative of a multivariable function. What we need to do is be more specific. To find the slope of a tangent line to a surface at a point, we must give that tangent line a direction. And in this video, we are going to consider what we call the x direction and the y direction. The x direction being the direction parallel to the xz plane, or essentially parallel to the x-axis, and the y direction being the direction parallel to the yz plane, or essentially the y-axis. Those are the two directions that we are going to consider when finding the slope of a tangent line to a surface at a point, at least for right now. We can look at other directions for tangent lines, but that comes later in Calculus 3. We're not going to worry about that for right now. And so let's take a closer look at these two directions. What does it mean, or what does it look like, to restrict the direction of our tangent line and just look at the x direction or the y direction when finding the slope? Starting with the x direction, to find the slope of the tangent line in the x direction, we have to contain it in a plane parallel to the xz plane, which is a plane that contains the x-axis. All right, so for example, as you can see here, I have drawn a plane that is parallel to the xz plane that cuts through the surface at the point where we want to find the slope of the tangent line in the x direction. All right, and when that plane cuts through the surface, what you get is a level curve for that surface that contains the point where we want to find the slope. And so then what we can do is find the tangent line at that point along the level curve, which there would only be one of, and that would be the tangent line that has the slope on the surface at that point in the x direction. Okay, that tangent line might look something like this. Unlike earlier, when we could draw an infinite number of tangent lines at this point on the surface, in this case there's only one that we can draw at that point along this level curve that results from containing it in a plane parallel to the xz plane. Okay, we have successfully restricted the direction of the tangent line at that point to be in the x direction. And when we do this, what this ultimately requires is that we hold y as a constant, okay? In this plane parallel to the xz plane, the y value never changes. If you look along the y-axis here, we never leave this particular y value. This plane would be represented by an equation y equals some constant, all right? And so this level curve that cuts through the point where we're trying to find the slope would be composed of points that all have the same y coordinate. Y would be held constant where the values of x can change, which then of course changes the value of z, the dependent variable. Okay, so by holding y constant, we force the tangent line to be in a plane parallel to the xz plane, which ensures that we are looking in the x direction. Now on the flip side, for the y direction, to find the slope of the tangent line in the y direction, what we have to do is contain it in a plane parallel to the yz plane. And so for example, take a look at this plane I've drawn here. This is a plane parallel to the yz plane that I've drawn such that it cuts through this point on the surface, creating another level curve, but this time where the tangent line to that curve at that point would be the tangent line in the y direction. It would be parallel to the y-axis. All right, so that tangent line might look something like this. This would be the only tangent line at that point along this level curve, which is in the y direction. All right, and when we do this, similar to when we're working in the x direction, how y is held constant, when we're working in the y direction, x is held constant, right? Looking in the y direction requires that x is held constant, which is what forces this tangent line to be in this plane parallel to the yz plane and thereby parallel to the y-axis, meaning it's in the y direction, right? This plane would be represented by an equation of x equals some constant. Along this entire level curve that results from cutting the surface with this plane, we have points that all have the same value of x, right? We do not leave this value of x right here along the x-axis. X is held constant for the entirety of this curve that contains this point, and so the tangent line to that curve at that point will be the tangent in the y direction. X is not changing, we're just focusing on y. Okay, so I hope this makes sense. This is conceptually what we need to do if we want to find the slope of a tangent line on a surface at a point in the x direction and the y direction. In order to find those two slopes, we have to give the tangent line a direction. We have to restrict it to one particular direction by containing it in a plane, either in a plane that holds y constant or in a plane that holds x constant. And this concept of treating one independent variable as constant and as a result forcing the tangent line to be in the direction of the other independent variable is what we call a partial derivative. In this case, either the partial derivative with respect to x, or in the x direction, or the partial derivative with respect to y, or in the y direction. Or really another way to think about it, if you remember from Calculus 1, a derivative of a single variable function could also be viewed as a rate of change, in particular the rate at which the dependent variable changes with respect to the independent variable. We can think of partial derivatives as being a way to determine the rate of change of a multivariable function, but with respect to just one of its independent variables, right? In other words, how does the output or the value of a function f of xy change with respect to x or with respect to y? We can look at the rate of change for those independent variables one at a time for the function. That is the idea of a partial derivative. And so more formally, here's how we define partial derivatives. For a multivariable function represented by z is equal to f of xy, so we are looking at a function of two independent variables here, this multivariable function has two different partial derivatives. There is a partial derivative with respect to x and a partial derivative with respect to y. A partial derivative with respect to x holds y constant, and it gives the slope of the tangent line to the surface at a point in the x direction. And notationally, we have a few options for representing that partial derivative. You could use one of these two notations, which looks similar to our notation for derivatives of single variable functions. If you remember dy dx, these would be the equivalent notations, but do notice that the d looks a little bit different. It's a little bit more curved. That is intentional. That more curved d indicates that it is a partial derivative. And so you could read this notation as the partial of f with respect to x, or you could just call it df dx. That's fine, but do note that those d's are a little bit more curved. Same thing over here. You could read this as the partial of z with respect to x, or just call it dz dx. Then another notation would be f of xy, but where you have a subscript of x for the function. So you'd have f sub x of xy. And if you want to, you can drop the xy part and just have f sub x, or you could also write this partial derivative as z sub x, since z is typically the dependent variable of a function of two independent variables. All right, just like how we use z here in dz dx. All right, so that is for a partial derivative with respect to x, but then for a partial derivative with respect to y, this derivative holds x as constant, and it will give the slope of the tangent line to the surface at a point in the y direction. And once again, notationally, you have a few options on how to represent this partial derivative. They're the same notations that we use for a partial derivative with respect to x, but of course those x's are replaced with y. So we have df dy or dz dy, or you could read them as the partial of f with respect to y or the partial of z with respect to y. Once again, note that those d's are more curved or curly compared to your typical derivative notation. But then you also have f sub y of xy, or removing the x and y, you just have f sub y or fy, and then also z sub y or zy. All right, these are all valid notations that you can use to represent a partial derivative with respect to y. All of these notations mean the same thing. They all represent a partial derivative with respect to y. Just like all of these notations mean the same thing, these refer to a partial derivative with respect to x. Okay, and so together, a partial derivative with respect to x and a partial derivative with respect to y for a multivariable function are what we call the first partial derivatives of that multivariable function. All right, so just like a single variable function has a first derivative, a multivariable function has first partial derivatives. And if you're interested, these two partial derivatives do have a limit definition, just like how derivatives of a single variable function have a limit definition. They look like this. The limit definition of a partial derivative with respect to x, or fx, is equal to the limit as delta x approaches 0 of f of x plus delta x, comma y, minus f of xy, all divided by delta x. And then for a partial derivative with respect to y, the limit definition for fy is equal to the limit as delta y approaches 0 of f of x, comma y plus delta y minus f of xy divided by delta y. All right, so remember from calculus 1, f prime of x is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x. This is the same exact thing we're using here, except we're working with a multivariable function and just focusing on one independent variable at a time. All right, so for the partial derivative with respect to x, notice that we're looking at the change in x. So we have f of x plus delta x, keep y constant, right? Y is not changing, there's no delta y. And so we take that function, subtract out the original, divide by delta x. Same thing over here. For a partial derivative with respect to y, we're looking at what happens when y changes. So we're looking at the limit as delta y. The change in y approaches 0. So we have f of x, where x remains constant, but then you're taking the change in y into account, y plus delta y, and then you're subtracting the original function and dividing by delta y. Okay, so everything we talked about before still applies here. A partial derivative with respect to x holds y constant, and a partial derivative with respect to y holds x constant. All right, but now that's enough about what partial derivatives are. Now let's actually get to the exciting part, which is how do we find these partial derivatives for a multivariable function? And so let's take a look at some examples. Okay, so here's our first example. We want to find the first partial derivatives of this multivariable function. We have f of xy is equal to 3x squared times y cubed minus 4x squared times y plus 5x squared plus 2y squared plus 3. All right, so remember, what we're going to do here is find two different derivatives, specifically two partial derivatives. For a multivariable function of two independent variables, what we want to find are the two partial derivatives, df dx, or the partial with respect to x, and df dy, or the partial with respect to y. And so let's start with the partial with respect to x. Let's find that first. So df dx is equal to what? Well, remember what we said about a partial derivative with respect to x. It will hold y constant. So what we do is take the derivative of this multivariable function where we treat all of the y's as constants. All right, so all of these y's that you see, just imagine that they're a constant and treat them as such. And so you'll just be taking a derivative with respect to x. So for example, take a look at this first term here, 3x squared times y cubed. You might look at that and think, oh, I have to use a product rule, but you don't. This is not an implicit function from Calculus 1, right? We're not doing implicit differentiation here. This is an explicit multivariable function in terms of x and y that we're just trying to take a derivative of with respect to x, where we treat all the y's as constant. Okay, so all you want to focus on here is that x squared part. Take the derivative of that x squared. And so remembering your derivative rules, you would need to use the power rule here, multiply that exponent down, and then subtract 1 from it. So you'll have 2 times 3, which is 6. So we get 6, and then x to the power of 1, because you subtract 1 from that exponent, and then just keep that y cubed as it is, right? That y cubed, we're treating it as a constant, so nothing changes there. It's just a constant being multiplied by some expression of x. So y cubed doesn't go anywhere. All right. And if it helps, if you're having a hard time visualizing this or understanding this, just try rewriting that term, but replacing y with a constant. Pick your favorite number. Let's say it's 2. You could rewrite that term as 3x squared times 2 cubed. And now think about how you would take the derivative of this. This is just a constant, so that doesn't really affect anything. You just use the power rule on the x portion and keep that constant multiplied by the result of that derivative. That's exactly what we've done here. We took the derivative of the x part and treated y as a constant. We kept it the same. All right, now let's move on to the next term. In this case, we have negative 4x squared times y. Once again, treat that y as a constant. Think of it as just some number multiplied by 4 that is also multiplied by x squared. And so taking a derivative here with respect to x, we'll multiply that 2 down and subtract 1 from the exponent. 2 times 4 is 8, so we get minus 8 times x to the first power, and then you multiply by y. Nothing happens to that y. We're treating it as a constant. All right, then moving on to the next term, there's no y's here, so this is pretty easy. Just take the derivative here with respect to x, as you would have done in Calculus 1. Again, multiply that exponent down and subtract 1, so you'll get plus 10x to the first power. And then moving on to the next term, what do we do here? We have 2y squared. Well, remember what we're doing. We're taking a partial derivative with respect to x, and there's no x's here, which means that this entire term is a constant term, right? We're treating y as a constant, so this whole term is constant, and the derivative of a constant is 0. So you would have plus 0 as the derivative of that term, and the same thing for this plus 3, that is very clearly a constant, and the derivative of that would also be 0. So you would be adding 0 twice there, but that doesn't really affect anything. Adding 0 doesn't change the value of something. And so this right here would be the first partial derivative with respect to x of this multivariable function. All right, so we found the partial with respect to x, but now let's find the partial with respect to y. Let's find df dy. What will that be equal to? Well, now this time we're taking a derivative with respect to y, so we're going to treat all of the x's as constants. All right, so in this first term here, 3x squared times y cubed, that x squared, just treat that x squared as a constant. It's just some number being multiplied by 3 that is the coefficient of y cubed. Okay, so to take the derivative here with respect to y, ignore the x, and just use the power rule for derivatives on y cubed. Multiply that 3 down, subtract 1 from the exponent, and you're done. So 3 times 3 gives you 9, and then you still have that x squared that does not change, and then you have y squared because you subtract 1 from the exponent. All right, then for the next term, we're subtracting 4x squared times y. Once again, treat that x squared as just a constant because we're taking a derivative with respect to y, and so you just have this coefficient times y to the first power. And remember that the derivative of a variable to the first power is just equal to its coefficient. All right, so the derivative of this term will be negative 4x squared. All right, just like the derivative of negative 4 times 2 squared times y would be negative 4 times 2 squared. All right, the derivative of y to the first power with respect to y would just be equal to its coefficient. That is exactly what we have done here. Okay, then moving on to the next term, 5x squared, there's no y's there. This is entirely in terms of x, but we are taking a derivative with respect to y, so this is entirely a constant. This whole term becomes 0. All right, so we get plus 0 when taking the derivative of that term with respect to y. And then for the next term, we have 2y squared. that is entirely in terms of y, so that should be a pretty simple derivative to do. Once again, just use the power rule for derivatives, multiply that 2 down and subtract 1 from the exponent, so you'll have plus 4 times y to the first power, and then the derivative of 3, that's a constant, so that will also be 0. So you could add 0 on the end here, but really we don't need those plus zeros, so let me just move that plus 4y right here, and there we have it. That is the first partial derivative with respect to y for this multivariable function. All right, and remember what we found here. For the partial derivative with respect to x, we have found a function that represents the slope of a tangent line in the x direction for a point on the surface represented by this function. And similarly, for the partial derivative with respect to y, we have found a function that represents the slope of the tangent line in the y direction at a point on the surface represented by this function. All right, so for a particular point on this surface, you could plug in the x and y coordinates into these two functions, and what you would get is the slope in the x direction and the slope in the y direction, respectively. Okay, let's take a look at another example. Here we once again want to find the first partial derivatives, and our multivariable function is f of xy is equal to e to the power of x times sine y minus e to the power of y times cosine x. Okay, so once again, there are two derivatives that we need to find here, two partial derivatives, the partial derivative with respect to x and the partial derivative with respect to y. Let's start by finding the partial derivative with respect to x. And just so that you get used to seeing different notations, this time I'm going to use f sub x to denote the partial derivative with respect to x for this function. And so what would that be equal to? Well, looking at the first term here, we have e to the power of x times sine y. And so be careful here. Again, this is not an instance where you need to use the product rule. E to the power of x is in terms of x, but sine of y is in terms of y, and we are treating y as a constant when we want to find the partial derivative with respect to x. All right, so sine of y here is just some constant value being multiplied by e to the power of x. Just think of it as a number like 2. We have 2 times e to the power of x. What would be the derivative of that? Well, the derivative of e to the power of x is just itself, and so then you would keep that constant. So nothing actually changes here for this first term. The derivative of that will just be e to the power of x times sine y. All right, but then moving on to the second term, we're subtracting e to the power of y times cosine x. Once again, we don't need to use the product rule here, because this part is in terms of y. We have e to the power of y, and this part is in terms of x. We have cosine of x. All right, so e to the power of y, we're just going to treat that as a constant. It's just some number multiplied by cosine x, which is the part we actually need to take the derivative of. And the derivative of cosine is negative sign. So this negative will become positive. We'll have plus e to the power of y times sine x. Okay, so you keep that e to the power of y as it is. It does not change. In this case, it's just a constant for that trig function that we took a derivative of. So that's the partial derivative with respect to x, but now let's find the partial derivative with respect to y, which we'll represent with this notation fy. What would that be equal to? Well, remember, now that we're taking a partial derivative with respect to y, we're going to treat the x's as constants. So for this first term, e to the power of x, that would just be a constant. It's some number multiplied by sine y, which is in terms of y, so we want to take the derivative of that. The derivative of sine is cosine, so what we get here for the first term is e to the power of x, that does not change, times cosine of y. Okay, again, we do not use the product rule here. This part is in terms of x, this part is in terms of y. This right here is the derivative of that first term with respect to y. Now moving on to the second term, we're subtracting e to the power of y times cosine x. That cosine x, we're just going to treat as a constant. So just take the derivative of e to the power of y, which would just be itself, so nothing changes here. You just get minus e to the power of y times cosine x. Okay, and so there we have it. Those are the first partial derivatives of this multivariable function. And remember, once again, what we found here are functions that represent the slope of the tangent line in the x and y directions respectively for a point on the surface represented by this function. Next up, we want to find the first partial derivatives for this function, which is given to us as an expression of the dependent variable z. We have z is equal to x times sine of xy squared. All right, and so let's start by finding the partial derivative with respect to x. And since we're working with z here, let's use this notation. Let's use z sub x, or zx, for the partial derivative with respect to x. And looking at the function we have here, we do need to use the product rule in this case, because you have x multiplied by a function that also includes an x. All right, x and the sine function are being multiplied together, and both of them involve the variable that we are taking a partial derivative with respect to, so you do have to use the product rule here. Okay, the first function being x and the second being sine of xy squared. All right, so remember the product rule from Calculus 1. If it's been a while, I'll have it up on the screen here for you to reference. But what you do is take the first function, which is x, and multiply it by the derivative of the second. And we're still taking a derivative with respect to x. All right, and we have sine of x times y squared. And so this y squared here, we will treat as a constant. Just think of it as some number times x. So it could be 2x or 3x or something like that inside of the sine function, which would be a function where we need to use the chain rule for derivatives. All right, the inside function being x times this constant of y squared, and the outside function being the sine function. So for the chain rule, I'll have that up here on the screen for you to reference as well. You start by taking the derivative of the outside function, keeping the same inside function, and the derivative of sine is cosine, so we'll have cosine of that same inside function, x times y squared, and then you multiply by the derivative of the inside function. And in this case, with respect to x, the derivative of this function, xy squared, will just be y squared, because if that's just a constant multiplied by x to the first power, the derivative of x to the first power would just be its coefficient, or the number being multiplied by it, which in this case is y squared. All right, so you're multiplying by y squared. Just like if we had 2 times x, the derivative of that would be 2. Same idea here, x times y squared, the derivative with respect to x will be y squared. All right, so that's the first term for the product rule. But now let's add the second term. We already took the first function times the derivative of the second, but now let's take the second function, which is sine of xy squared, and multiply it by the derivative of the first. And in this case, the derivative of x with respect to x is just 1. All right, the coefficient of that x to the first power is just 1. All right, and so then simplifying, this would be equal to x times y squared times cosine of xy squared plus sine of x y squared. All right, I just reordered the multiplication here. I like to group together the x's and y's and pull them out front of the other function. Technically, you don't have to do that, but that's how I like to do it to keep things organized. And so that right there would be the partial derivative with respect to x for this function. But now let's find the partial derivative with respect to y, or z, y. What would that be equal to? Well, remember, now we're going to be taking a derivative of this function with respect to y, so we're going to be treating x as a constant. So this x is a constant, and this x is a constant, which means that we're not going to be using the product rule here, right? The variable that we're taking a derivative with respect to is not found in both of those functions like it was earlier, right? X is here and x is here, but y is only here inside the sine function. So this x is just some constant being multiplied by sine of another constant times y squared. So we don't need to use the product rule here, but we will need to use the chain rule because you have sine of another function. All right, the inside function here is x times y squared, and the outside function is sine. So to take the derivative here, you keep that same constant on the outside, so we still have x, but then you're multiplying it by the derivative of the outside function, and the derivative of sine is cosine, so we get cosine of that same inside function, xy squared, and then you multiply by the derivative of the inside function. In this case, we're treating x as a constant and taking the derivative of y squared. So we'll multiply the 2 down and subtract 1 from the exponent, giving us 2x times y to the first power. All right, and so now, if we simplify, you can multiply these two x's together and get x squared. And so bringing this all out front, this would be equal to 2x squared times y times cosine of xy squared. And that right there would be the partial derivative with respect to y for this multivariable function. All right, and so there we have it. These are the first partial derivatives of this function. So you could plug in the x and y coordinates for a point on this surface into these two functions to find the slope of the tangent line in the x direction or find the slope of the tangent line in the y direction. All right, let's take a look at one more example, and this is a fun one. Hey, real quick, before we get to the next part of this lesson, if you find my videos here at JK Math to be helpful, then I'd like to invite you to join my membership site JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out, as it's a great way to support me in the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. Okay, so for this example, we want to find the first partial derivatives and the slopes in the x direction and y direction of the surface at the point 2, 2, 4. And our given surface is z is equal to x to the power of y. And so let's start by finding the first partial derivatives. I'm going to use one of the notations we haven't used yet, which is this notation. For the partial derivative with respect to x, we'll have dz dx. And so what we want to do is take a derivative of z with respect to x. So we're going to treat y as a constant. And that's pretty interesting, because if we treat y as a constant, what are we working with here? Well, we just have x raised to the power of some number, which we would take the derivative of by using the power rule for derivatives, right? It's just as if we had x squared, or x cubed, or x to the power of 4, or any other number. When you take the derivative of x to a constant power, you multiply that power down and subtract 1 from it. So in this case, if we're treating y as a constant, we will do the same thing here. We'll multiply y down and subtract 1 from y. So what we get here for the partial derivative with respect to x is y times x to the power of y minus 1, which seems really weird, but that would be correct. This is the partial derivative with respect to x. Since we're just treating y as a constant, we make use of the power rule for derivatives. All right, but now what about the partial derivative with respect to y? In this case, that would be dz dy. Well, now we're going to be treating x as a constant, so we have a constant raised to the power of y. That would be an exponential function, right? Think of it as 2 to the power of y, or 3 to the power of y, or any other number to that power of y. Okay, and so remember how we take the derivative of an exponential function like that. We simply rewrite the exponential function and then multiply by the natural log of the base. So we'll have the natural log of x, since x is the base. All right, it's no different than if we took the derivative of 2 to the power of x, right? d dx of that expression would be 2 to the power of x times the natural log of 2, 2 being the base. Or even when you're taking the derivative with respect to x of e to the power of x, it's the same thing. That's equal to e to the power of x times the natural log of e, but the natural log of e is just equal to 1. So you have 1 times e to the power of x, which is just e to the power of x. All right, so that is how we take the derivative of an exponential function, which is what we would have here if we're treating x as a constant. All right, so our answer is correct. This is the partial derivative with respect to y for this surface. And so those are the first partial derivatives, but now let's use them. We want to find the slopes in the x direction and y direction of this surface at the point 2, 2, 4. And so we'll get the slope in the x direction by using the partial derivative with respect to x, and we'll find the slope in the y direction by using the partial derivative with respect to y. All we have to do is plug in the x and y coordinates from this point into those derivatives. All right, so let's start with the slope in the x direction. We're going to take dz dx and evaluate it at the x and y coordinates of 2, 2. And this is the notation for that, by the way. When you're using the notation with the curly d's, this is how you write out that you're evaluating it at a point. If you were using one of the other notations, like f sub x, you would just have fx of 2, 2, and then plug in. All right, so those are a little bit easier to work with. But if you're using this notation, this is how you denote that you're evaluating it at a point. And what do we get here if we plug in 2 and 2 for x and y? Well, just replace each x and y in this expression with 2, and you'll get 2 times 2 to the power of 2 minus 1. And 2 minus 1 is 1, so this is equal to 2 times 2, which is 4. So 4 is the slope in the x direction on this surface at this point. But now let's find the slope in the y direction. We're going to take dz dy and evaluate it at 2, 2. So plugging in 2 for x and 2 for y, we get 2 to the power of 2, or 2 squared, times the natural log of 2. And 2 squared is 4, so this just becomes 4 times the natural log of 2. That right there would be the slope in the y direction on this surface at this point. All right, and as an approximate value, if you put this into your calculator, just to get an idea of what that value is, it's approximately 2.77 and some more decimals. All right, so the slope in the y direction is smaller than the slope in the x direction at that point on the surface. Now, this was the last example of finding partial derivatives for multivariable functions of two independent variables, but we can't close out this lesson without also mentioning that you can find partial derivatives for functions of three independent variables, or functions that have even more independent variables than 2 or 3. And so let's take a closer look at that. If you're working with a multivariable function of three independent variables, such as w is equal to f of xyz, then what you can do is find a partial derivative for each of the three independent variables. In this case, the independent variables are x, y, and z, so you can still find a partial derivative with respect to x, as well as a partial derivative with respect to y, but now you can also find a partial derivative with respect to z, since z is now an independent variable. In this case, w is now the dependent variable. All right, so because of that, the meaning behind these partial derivatives is slightly different, but the main idea still holds. Specifically, for a partial derivative with respect to x, you will be differentiating with respect to x, which means that you will hold y and z constant in those derivatives. And so the different notations here would be df dx, dw dx, since w is now a dependent variable, and then fx of xyz, or fx or wx. Then for a partial derivative with respect to y, you would take a derivative with respect to y, holding x and z constant. And so then the notations would be df dy, or dw dy, fy of xyz, or fy or wy. And then for a partial derivative with respect to z, which is new here, you would take a derivative of your function with respect to z, holding x and y as constants. And so the notation here would be df dz, or dw dz, along with fz of xyz, or just fz or wz. Okay? And so together, these are the first partial derivatives of a multivariable function of three independent variables. But this can be extended to functions of more than three independent variables. You just have to remember that to find a partial derivative with respect to one of the independent variables, you need to hold all the other independent variables constant and differentiate with respect to the variable of interest. All right, and that's exactly what you see going on here. The partial with respect to x holds y and z constant, the partial with respect to y holds x and z constant, and the partial with respect to z holds x and y constant. Okay? And what these represent can be a little bit harder to visualize as you work with functions of more and more independent variables, because this function of three independent variables represents a four-dimensional shape, which we don't know what that looks like, but you can still think of each of these derivatives as being the slope in a particular direction for whatever shape that function represents. All right, so the partial with respect to x is still the slope in the x direction, the partial with respect to y is still the slope in the y direction, and then the partial with respect to z is the slope in the z direction. All right, again, it's not easy to make sense of or to visualize because we would be working in four dimensions, but everything we talked about earlier can be extended to these functions of more independent variables. Okay, and so to end this lesson, let's take a look at one example of finding the first partial derivatives of a function of three independent variables. Okay, so what we have here is w is equal to 4x to the power of 5 plus 2xy minus 3yz plus z to the power of 3. And of course, we want to find the first partial derivatives. In this case, there will be three of them because this is a function in terms of three independent variables, that being x, y, and z. All right, so let's start by finding the partial derivative with respect to x. We'll represent that with w sub x, or just wx, and that will be equal to what? Well, we need to take the derivative of each of these terms with respect to x treating all the other variables as constants. So any y's or z's that you see, you're going to treat them as a constant. So with this first term, all you see is x, so this is pretty simple. Just use the power rule for derivatives, multiply that 5 down, subtract 1 from the exponent. 5 times 4 is 20, so you get 20 times x to the power of 4. Then for the second term, we have 2xy. Remember, we're differentiating with respect to x, so hold y constant, treat it as if it were any other number. It's just some constant times 2 times x to the first power, and the derivative of x to the first power is just equal to its coefficient, or the numbers being multiplied by it. In this case, that would be 2y. All right, so we're left with 2y. And then for the next two terms, there are no x's. We're differentiating with respect to x, and so if there are no x's in those terms, they are essentially constants, and the derivative of a constant is 0. All right, so we could add 0 and add 0, but that's not really necessary. That doesn't affect our answer. This would be the partial derivative with respect to x. It's 20x to the power of 4 plus 2y. Now let's find the partial derivative with respect to y. So we're going to be taking a derivative with respect to y and treating x and z as constants. And so right away with this first term, there are no y's. It's just 4x to the power of 5, and we're treating x as a constant, so this whole term is a constant, so the derivative is 0. So you could write down 0 and then add the derivative of the following terms, but that's not really necessary, so I'm just going to erase that and move on to the next term where we have 2xy. And in this case, we're treating x as a constant, so 2x is just the coefficient of y to the first power, so the derivative of that would just be equal to its coefficient. So the derivative of this term with respect to y is 2x, and then we want to take the derivative of this term, minus 3yz. Remember that z we're treating as a constant because we're taking the derivative with respect to y, so this is very similar to the derivative we took over here. Negative 3 and z are just constants being multiplied by y, and the derivative of y to the first power is just equal to its coefficient. So we'll just be left with minus 3z. And then for the last term, there are no y's in it. It's z to the power of 3, or z cubed. And so with respect to y, that is a constant, and its derivative is 0. So once again, you could have plus 0 on the end there, but that doesn't affect our answer. wy, or the partial with respect to y, is 2x minus 3z. And finally, let's find the partial derivative with respect to z. What would that be equal to? Well, remember, we're going to be taking a derivative with respect to z now, so we will treat x and y as constants. So these first two terms have no z's in them, right? We just have x's and y's. So with respect to z, these two terms are constants whose derivatives are 0. So these two terms become 0, which you could write down if you wanted to, but I'm just going to move right on to the next term here, where you have z to the first power, and everything else is a constant being multiplied by that. So the derivative of z to the first power would just be equal to its coefficient, which includes y because we're treating it as a constant. So we get negative 3y for the derivative of that term. And then for this last one, the only variable present is z, so just take a derivative as normal, use the power rule and multiply 3 down, and subtract 1 from that exponent, and you'll get plus 3z squared. Okay? And that would be the partial derivative with respect to z for this multivariable function. And so if you wanted to know the slope on this function in the x, y, or z directions, you could plug in the coordinates of x, y, and z for the point into these functions and get the appropriate slope. Okay? And so with that, that is it for this lesson. But if you do want to get some more practice finding partial derivatives, be sure to check out my examples video for this topic that I'll have linked here on the screen. If you have any questions, please let me know in the comments. But if you don't have any questions, this is all I had for now, so I will see you next time.